All right, everyone. So I want to finish this proof, actually give a complete proof that the square root of x is uniformly continuous on its domain. And in class, we kind of outlined a three-step process that actually would work really well if we were able to use that theorem. So kind of the idea of that proof was to kind of first work on a closed interval and say, well, since we're on a closed interval, say from 0 to 5, we know that by the theorem that says any continuous function on a closed interval is uniformly continuous, that means there's got to be one delta that works for all of these possible points in here, right? And then maybe as a separate proof, we would show that there's going to be some delta that works maybe on all the other points. So maybe for all the other points, we do a separate problem. We find that there's one delta that works for all inputs way out here, and then we know that there's going to be a delta that works for all of them. Right? And then in class we kind of started with what was actually the really hard part of this, which is dealing with that kind of vertical tangent line at 0. So this is quite a bit of work, and you saw me struggle to try and give motivation and really struggle with how to kind of best present this. And I've had some time to kind of think. I did a little research online, kind of see what maybe the cleanest way to do it was. And actually, I want to just do this all in one go. And so I'm going to show that there's a delta that works at all of these things, and it's actually going to be a very simple, beautiful formula for delta in terms of epsilon, right? And so how might we discover that? Well, let me show you that. So we start with an epsilon. We got to find first. Maybe let's focus on the hard point. If we focus at 0, we want to find a delta that works there. And so what we're going to need is well, hey, if x minus 0 is less than delta, so if x is less than delta, then we're going to need f of x minus f of 0 to be less than epsilon. So we're looking for some number delta that would guarantee that if x is less than delta, then the square root of x is less than epsilon. And I think you look at that and you say, oh, well, how about epsilon squared? Right? I think that's perfect, right? Because now if this is less than delta, then that's going to be less than epsilon squared. Take the square root of both sides. Square root of positive numbers, it preserves inequality. It's because square root is an increasing function. That's going to be perfect, right? And so we have found a delta, and where does it work? Well, so far we've only proved it at 0. And so now what we might do is we might get Desmos open, we might check that, we might say, wait a minute, I think epsilon squared actually works at quite a bit of numbers. It seems to work not just at 0, but maybe it works for numbers really close to 0. Maybe it works for all numbers, right? In fact, if you think about it, the hardest place to find delta is going to be at 0. And as we move to the right in our picture, because the graph is getting less steep, it's going to be more and more easy for a particular value of delta to work. And so let's see if we can do that. So in fact, delta equals epsilon squares works for all points x0 in this range. And the proof of this requires a slightly clever trick, but it's not so bad. Right? And so let's assume that x minus x naught is less than delta. Okay. So, i.e. that's going to mean that x minus x naught is less than epsilon squared. Okay. And then what do I want to show? Well, I want to show at the end of the day, I'll put this down here with my want to show. I want to show that f of x, which is square root x, minus f of x naught, which is square root of x naught, I want to show that this is less than epsilon. And how could that be true? Well, I look at it, and And I say, well, you know, if it so happens that the square of this was less than epsilon squared, then because I have two non-negative numbers, I could just take the square root of both sides, and I would be able to conclude that, right? So that's like one of the like just little bits of insight that we might need. And I look at that and I say, well, wait a minute, maybe I can prove that. Maybe that's something I can actually show. And so, actually, let's get rid of our want to show. Let's get rid of this, because we need to show that. And let's see if we can get there. So let's see if we can prove that x, square root of x minus square root of x naught, let's see if we can show that, when we square it, is less than epsilon squared. Right? And so what I'll do is I'll start and I'll say, well, this is square root of x minus square root of x naught. And I take the absolute value of that, and I multiply this times square root of x minus square root of x naught. Right, no big deal, I just wrote out the square root. And now, I want us to look at this, and I want us to now use the triangle inequality on this. I want us to use the triangle inequality on this and say that this is going to be less than or equal to, I'll rewrite the first factor, I'm not changing that, times square root of x plus that. Right? And so let's review just kind of what the triangle inequality says. It says if I have the absolute value of a minus b, well, that should be less than or equal to the absolute value of a plus the absolute value of b. Okay? And so if I apply that in this case, well, what's a? Well, it's going to be this. And what's b? Well, it's going to be the other factor. And you say, what happened to the minus sign? Well, it becomes a plus. Right? It becomes a plus because I'm taking the absolute value of like minus b, which is just the absolute value of b. And so what happens here is I get the sum of two numbers. They're both positive, so I really don't even need absolute values, but I'll keep it around the whole thing. And that is where this inequality is coming from. Right? So you may want to pause the video and double check that. Alternatively, what you may want to do is you might just want to think and say, well, wait a minute, I've got two numbers. At this side, I'm subtracting them and looking at their difference. And here I'm adding them together and then taking their absolute value. You know, since I've got positive numbers, adding them together is going to be way bigger than subtracting them. Right? I mean, I guess it all depends on how apart they are, but generally we should it should be okay that's going to be an inequality. And now this epsilon squared, we're still not ready for it. So what do we know now? Well, let's just multiply. If I multiply these together, what do I get? Well, I could FOIL it out. FOIL, 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 FOIL. And when I FOIL it out, I get x minus x0. It's the factoring, actually, of difference of two squares. And so what do I get? I get x minus x0. I guess I better keep the absolute values around it. And what did I know about that? I knew that that was less than epsilon squared. I knew that was less than epsilon squared. Right? So therefore, I'm just going to extract the first term, so the term on the far left, and the term on the far right. And then I'm going to take the square root of both sides. And I have gotten my conclusion. And so therefore, this delta works for any 2 points. Right? Because now I've got no assumptions. So now no matter, so I guess I should have said this here. So let x and x naught be in from 0 to infinity. Then now this proof just carries through completely. So thanks for watching. This isn't one of my favorite ways to prove this. So full disclosure, I don't like proofs like this that are kind of where they've got like a cool trick, or you have to kind of think of factoring or something like this. The way I really would recommend to do it is is by using that theorem that we had in class. And so maybe now I'll just kind of sketch how that would go. So if you are like me and maybe you struggled, as you saw me in class struggle to kind of do this proof, let me just show you another way that I might do it. Right? And so let's consider the function f of x equals square root of x. And step 1, I am going to use the theorem from class that says that since f is continuous on 0 to 5, which is a closed interval, f is in fact uniformly continuous on 0, 5. Okay. So I should probably start with an epsilon. So therefore, there exists a delta that works on for all points. So it works for all points x naught in 0 to 5. Okay. So again, it's a big black box. It's using a theorem that does that, but the theorem takes care of this really pesky kind of point at 0 for us. Right? And so now we have a delta that works at all those points. Let's actually call it delta 1 because we're going to find a different one. And so now let's find a delta that works for all x naught from, well, we could go from 5 to infinity, but just to be safe, let's go from 3 to infinity. And let's call it delta 2. Okay. And so now we're going to have a much easier time, and our brains can kind of do all of the lifting without for need of clever tricks. So now what we can do is I will maybe set up my proof. So I need to find a delta. And then what I need is that if x and x naught are in this range from 3 to infinity, and the distance between them is less than delta, then I need to conclude something about the distance between f of x and f of x naught, which again we've seen is just square root of x minus square root of x naught, which is equal to, I can now rationalize the numerator. I can multiply top and bottom by this expression here. Right? And you may say this is similar to that trick we did in the earlier problem, but this trick is a little bit more natural because we've done it a lot. We do it a lot in calculus. And when we do this, we get in the numerator x minus x naught over x plus x naught with square roots. And of course, this is now less than delta over this thing here. And now we're in really good shape. Because now x and x naught, they can't be close to 0. They have to be at least 3. Right? And so if I think about that, what that means, well, if they're at least 3, let's see. So if x and x naught are at least 3, right, then square root of x and square root of x naught are going to be at least, well, they're at least the square root of 3. But that's, that's bigger than 1. So I'm just going to use the fact that they're at least 1. Oh no, map of San Diego. I'm just going to use that. And so then when I take their sum, that means their sum is going to be at least 2. And so when I do this fraction, this is going to be no bigger than delta over 2. Okay. And so my reason for this is going to be here. And now, what do I let delta 2 equal? Well, I guess I have it equal to 2 epsilon. And so where did I use this? Well, if I let that be 2 epsilon, then that's going to work. And so now what do I have? Well, from the interval from 0 to 5, I have a delta 1 that works for every point. I don't know what it is because I use this black box of a theorem. But I know that there's some number that works. Maybe it's epsilon squared, actually. Maybe that's what that theorem supplied us. Who knows? But then I found an explicit delta 2 that works for all the other points. And so now we have one delta that works for numbers between 0 and 5, one that works for any number greater than or equal to 3. And so now if we just take the smaller of those two deltas, it will work for every possible number. Okay. And so now if we let delta equals the minimum, delta 1 and delta 2 will work for all x naught between 0 and infinity. So therefore, square root of x is uniformly continuous on this set. So we've seen two different proofs, one that explicitly gave a delta, and the other that kind of used that big theorem and then solved a slightly easier problem on a different subset. So thank you for watching. Happy Friday, and I will see you soon.